And so what we're going to talk about today, yeah, go ahead and get your participation point for this one. So enter that number into Top Hat. But the ultimate thing that we can do with this kind of information is we can actually use it to solve problems. And these are kind of realistic problems that get encountered in the chemistry lab from time to time. So one thing that we can do, one common problem that we often run into is a matter of identification. I do this reaction in the laboratory. I have a rough idea of what is in the compound, but I have no idea what its chemical formula is. Or I'm given this unknown substance and I can run some preliminary tests on it to figure out what is in it, but I have some trouble trying to determine what the actual chemical formula is. Now, the way that we can solve this is by determining something called the empirical formula. The empirical formula for any compound is simply the smallest whole number ratio of each element to each other in that compound, in that molecule. This is different from the molecular formula. Thus far, all that we've really talked about have been molecular formulas. When we describe the chemical formula of a substance, we're talking about the molecular formula of that substance usually. And so there are occasions where we have seen where it isn't a whole number simple ratio, but rather a multiple kind of ratio going on there. And that's how we can tell the difference. Now, some empirical formulas are also molecular formulas. But what we see, especially in organic chemistry, where we're dealing with biology molecules, when we're dealing with sugars, when we're dealing with more complicated kinds of structures, kinds of molecules, what we tend to find in those cases is that the empirical formula usually represents a very simple relationship, and that the actual substance itself is far more complicated. Now, what does any of this have to do with mass percent? Well, mass percent is one of the most common ways that we can determine something about an unknown substance. So there are different kinds of machines out there. One's called a mass spectrometer. And a mass spectrometer can do a couple of interesting things. First of all, it can tell us what the overall molar mass is for a particular compound. It can also tell us how that particular compound breaks down. And there are other kinds of analysis that exist that can give us mass percent compositional data and tell us, okay, this particular substance is 30% carbon and 25% oxygen and 55%, 45% fluorine, for example. And from those data, we can actually do some pretty simple calculations that you actually have already done to figure out what the actual substance is and what its formula is. And so the process to do so is right here in front of you. Now, it looks complex. Anytime you see something listed out as a series of steps, it looks a lot more daunting than it actually is. Good thing is we're going to do several examples here. And once we do some of the examples, you'll see that the steps always follow a certain pattern. And once we kind of get a good sense of what that pattern is, it's actually not that hard to follow the process because we've already done most of the steps in this process already. But the big key in this process overall is I have to be able to turn my numbers, whatever they may be, into whole numbers. Because that's what our chemical formulas are given to us in. They're given to us in whole numbers, whole number ratios of one element to another. So the way that I do that is in some kind of form or fashion, I need to start with grams. I need to start with mass of each element that makes up this compound. And this is where mass percent data can be really useful. Because if we take mass percent as being a part of 100, what we can see is that that mass percent data actually can give us a number of grams if we think about our sample as being a 100 point kind of sample. So our first step always is to get our stuff into grams. So if we have experimental data, it's probably already in grams. If we have mass percent data, all what we do is we just change the unit from percent to grams. So if I'm told that I have 33% carbon, my first thought is just to turn that 33% into 33 grams, and then I can move on. I do that for every single element in the sample. The second step is something that you already know how to do. We're going to turn the masses into moles using molar mass. Something we've been doing all week here. The third step is a little bit funky, but what we're doing is we're doing standardization. And what I mean by standardization is the end goal is I need to get everything to whole numbers. The simplest whole number is 1. And so what I'm going to do is I'm going to use whatever element was my lowest total, and I'm going to make that 1 by dividing everything by that number. And then hopefully all my other mole numbers will kind of work themselves out once I do that division. So there are a couple of steps that we can take to account for those adjustments, where we either just simply round up or round down if we're close enough to the whole number but not actually there. Or if we note that there's a fraction present, we can multiply everything by the denominator of that fraction to get everything into whole number terms. But like I said, this part can be kind of sketchy looking without examples. So let's do some examples. So I have an unknown organic solid that has these 3 elements in it: carbon, hydrogen, and oxygen. Those 3 elements are present in the amounts shown. Question is, what is the empirical formula? So we need to go through the steps of the process here. So the first step in the process, I'm going to turn all of these percents into grams. So 75.73% turns into 75.73 grams of carbon. 8.74% gets turned into 8.74 grams of hydrogen. 15.53% gets turned into 15.53 grams of oxygen. So all I've done in this first step is just taken those percentages and converted them into grams. And what I'm using there is basically just the definition of percent. Percent means part of 100. I can turn those into grams by pretending I had 100 grams of the sample. Now, does it matter that I don't have 100 grams of the sample? No, because those percentages would apply to whatever value I had. I could just multiply it if I wanted to. But in this particular case, I don't need to, because the ultimate goal is the ratio of the elements to each other, not how many grams of each one I actually have. So that's my first step. Second step, I needed to convert these into moles. To convert grams into moles, I use the molar mass. So 12.01 grams of carbon in a mole. So I do the division, 75.73 divided by 12.01 to 4 sig figs, 6.306 moles. Want to do the same thing for the hydrogen? 1.01 grams of hydrogen in a mole. So 8.74 divided by 1.01 is going to give me 8.65 moles of hydrogen. For the oxygen, 16.00 grams of oxygen in a mole. So 15.53 divided by 16.00, 0.9706 moles of oxygen. So this is an important step because if I'm trying to compare things atom to atom, I can recognize that comparing things mole to mole does the same thing because moles describe the same amount of atoms regardless of element. Now, right now, I don't have anything that closely resembles whole numbers in any form or fashion. So I'm going to have to do a standardization step. This is always the next step. How do I standardize? Well, I need to take my smallest number and make it 1. I do that by dividing it by itself. Now, general rules of algebra tell me that if I do something to one item, I need to do the same thing to all of the items so that it stays even. So I divided the bottom by 0.9706. I need to divide all of them by 0.9706. So 6.306 divided by 0.9706 is going to give me 6.497 moles of carbon. 8.65 times or divided by 0.9706 is going to give me 8.91 moles of hydrogen. Okay. Neither of these look great, but they're a lot closer to whole numbers than we had originally. And so here's where we want to go back to those guidelines that we saw on the previous slide. So clear this up just for a second. Any number within 0.15 of a whole number, we can round to that whole number. So we had that 8.91. 8.91 is close enough to 9 that we're going to call it 9 and be pretty confident about it being 9. Now, the 6.497, we're not really close to any whole number there. We're kind of smack dab in the middle. And so that's where the second bullet point comes in. If we have a known fraction, 6.497, that's pretty much 6.5. If I have a half, I'm going to use the multiplier of 2 to get rid of the half. And it's the same thing that we saw in the previous point. So we're going to round this to 6.5, this to 9, and that's going to stay at 1. To get rid of the half, I need to multiply it by 2. If I multiply this one by 2, I've got to multiply the others by 2. So in the end, I'm going to have 13 for carbon. I'm going to have 18 for hydrogen. And I'm going to have 2 for oxygen. So my overall ratio would give me a chemical formula: carbon 13, hydrogen 18, oxygen 2. Can I reduce any of those numbers into simpler terms and keep everything a whole number? No. The closest thing I have is the 2. I can divide the 2 into 18, but I can't divide the 2 into 13. So this is an empirical formula, albeit a very large and kind of complicated one. But the reason I chose this particular example is because it kind of highlighted every possibility that exists. We had to do a standardization. You'll always have to do a standardization. We had to do a rounding. Sometimes you have to do this, sometimes the numbers are very, very even. We had to do a multiplication. Depends on the scenario. Will you have to do all of those in one problem? Hopefully not. Again, this is kind of the most complicated example I could give you to show you all the different things that could happen, but hopefully won't. So that's the empirical formula. Now, empirical formulas and molecular formulas are different from each other. How do I know what to do as far as a molecular formula is concerned? Well, in that particular case, what we have to know is we have to know something about the actual substance itself. And so the information that we are being given here about the molecular formula, this is the missing piece. What we are ultimately trying to do is we're going to compare this substance with this mass and see if they are related to each other in some kind of way. So if I was going to take the molar mass of our empirical formula, 13 carbons times 12.01 plus 18 hydrogens times 1.01 plus 2 oxygens times 16, I get 206.31 grams per mole. What I can see from my calculation is that my empirical formula is not the molecular formula. The two masses are pretty different from each other. Now, if you've got some mental math skills, you can probably look at this and say, oh, it's double. And yeah, you'd be right, it's double. If you weren't so sure of that, the way that we can calculate a multiplier is by taking the molar mass of the molecular formula and dividing it by the molar mass of the empirical formula. And whatever that number is, we round it to the nearest whole number. That would tell us what we need to take the empirical formula and multiply it by to get the molecular. So molecular mass is 412.26. The empirical mass was 206.31. If I divide those by each other, I get 1.9983, which round that to the nearest whole number, it's 2. And so the molecular formula is going to be double the empirical formula. So it'd be C26H36O4. I just take each of those subscripts that make up my empirical formula, and I just dump. Because my multiplier was 3, I would triple all the values. My multiplier was 4, I'd multiply all the values by 4. In this case, however, it's just 2. Right, so any questions about kind of the process here? I know, kind of moving through it quick. One of the things about having only 25 minutes to do something that has a lot of calculation steps to it. All right, let's take a look at one more example and we'll call it a week. So this one is just asking about empirical formula. It's not asking about molecular. I've got 13.77% magnesium, so I'm going to turn that into grams. I've got 31.83% silicon, so I'm going to turn that into grams. I've got 54.39% oxygen, so I'm going to turn that into grams. So the first step in each of these would be to turn the grams into moles using the molar mass. So molar mass of magnesium is 24.31 grams. So 13.77 divided by 24.31 is 0.5664 moles. The molar mass of silicon is 28.09. So 31.83 divided by 28.09 is 1.133. And then oxygen is 16. So 54.39 divided by 16 would give me 3.399 moles of oxygen. So once again, you can see we don't get whole numbers out of the first step. We're going to need to standardize. Standardization, we divide by the lowest number in each case. So this time it's the magnesium. So that's going to give us 1 magnesium. 1.133 divided by 0.5664 is going to give us 2 silicon. 3.399 divided by 0.5664 is going to give us 6 oxygen. So in this particular case, I don't need to do any additional rounding. I don't need to do any additional multiplying. The standardization has already given us whole numbers. And since I'm already at the whole number stage, I just need to write the formula that represents those ratios. So a couple of things that I'm going to give you. First of all, if you want more worked out examples, I'll give you a link to another talk that I did that has more examples worked through in it, so that you can kind of work through them and kind of work along with them. I'll also post if you want to work through the PowerPoints, and the examples in the PowerPoints yourself and check them against something, I will post the completed versions there as well in Blackboard. On your way out, as we end out this week, just get your last participation point of the chapter. So put that in on your way out before you go. Have a great weekend, and I will see you when I get back. Dr. Peralta will be here on Monday to take you through equation balancing. Have a great weekend.